We're going to solve this problem by describing the vector algebra that follows the position of the car A and car B with respect to a global frame of reference that is fixed on the ground called N. So this would be the x-axis for the frame N, and this is the y-axis for the frame N. As our car A moves along the circular path, its orientation is going to change. And we can describe that orientation by using a local frame of reference, a frame that moves with the object, that also has a horizontal and vertical axis. Let's call this one x a hat and y hat a. So when the car is in a different position, for example this one, we have the x a axis and the y a axis pointing into a different direction with respect to our global xn and yn. Same for this orientation, that it has a new direction for xa and for ya. Since the car moves in a circular motion, we can now think of a relationship between xa and ya and xn and yn as just the change of angle between the two frames. I will draw the frames again separately for this to be more evident. So I will draw the frames again here. We have the xn axis and the yn axis for our frame n, and we have the frame A with its corresponding x-axis and y-axis, and between the xa axis and the xn axis there is an angle theta that will change in time following the motion of the red car. Thus we can write a vector that goes from the origin of the system in the center of the track to the current position of the car, and we can describe that vector RA as an scalar distance of 16 meters, which I will write RA scalar, in the direction of vector XA. As you notice, if the car keeps moving, our frame A and the corresponding axis XA will change directions, making our new RA following always the direction of XA. So the vector RA is RA scalar times x hat a vector or unit vector that points to the red car and follows a change of angle, a corresponding change of angle theta. Now let's think about the x hat a unit vector described in terms of the xn and the yn unit vectors. We can try to use some simple trigonometry here and project the horizontal component of xa and the vertical component of xa so that we compute the component in the direction of yn and in the direction of xn, such that x hat a is equal to sine, let's start with cosine theta in the direction of xn plus sine theta in the direction of yn. So the first component is this component, the second component is this component right here. We can try to do the same with ya. You can pause the video for a second and try to do it yourself and see if you get the same result that I do. So let's do the component of ya by looking at this angle theta here. We can see that the projection on the horizontal axis is negative in the direction of xn, so it's in this direction, and is the length is sine of theta. So now we have a component minus sine of theta in the direction of xn plus cosine of theta in the direction of yn. So this component right here.